In this video, we're going to do a little bit of a check on some of the terminology we use, and then we're going to do one very simple example and then one more complicated one. So first off, we've been using this term power series a lot lately. It refers to an infinite polynomial. That's it. We've seen a lot of them. Anytime you have a polynomial where you just keep adding terms and terms forever and ever and ever, and usually write it with sigma notation, that is called a power series. Now, when we're using a power series as a way to approximate a function, really approximate's not the word, we're using a power series to rewrite a more complicated function, like turning e to the x into an infinitely long polynomial, something like that. We call it a Taylor series. Now, so far, we've only looked at Taylor series where we use x equals 0 as sort of home base and build around x equals 0 going in both directions. It doesn't have to be that way. So a Taylor series could have another x value there, and that's what the two examples in this video are going to be like. But just so you know, there is a name for the Taylor series we've been doing where it's always centered around x equals 0. And these are, the easier ones. They're called the Maclaurin series. I know it sounds like, oh no, that's a special type, that must be extra hard, but no, the Maclaurin ones are the easy ones. We like those. So make sure you read directions carefully if you're asked for a Maclaurin series, or if you're asked for a Taylor series centered on x equals 0, that's the good kind, that's the easy kind. In this video, we'll look at some others. And just so you know, the Taylor series is infinite. If we're only looking at a few terms of the Taylor series, like so say you were asked for the first 3 terms of the Taylor series, that would be called a Taylor polynomial if you're only looking at a finite number of terms, not an infinite number of terms. And that's why you might see this terminology sometimes. Okay, so let's look at a simple example here. We're going to look at a function that has this behavior at x equals 2. Its value is 1, its derivative is 3, its second derivative is -1/2, its third derivative is -2, and every derivative higher than that, so the nth derivative for every n bigger than or equal to 4, is 0. We're going to write a Taylor series centered on x equals 2. Now, in order to do that, what we're going to do is equate derivatives. That's the process we've been doing, saying that we want f of 2 to equal p of 2. Right? Our p is our polynomial. That's our Taylor series. We want f of 2 to equal p of 2. And the idea here is that we want p of 2 to just equal that first constant, that's c0. And the first derivative of 2 we've seen is that first coefficient. So right here we've said we want these to be equal, so c0 is going to be equal to 1, c1 is going to be equal to 3. Now is where it gets a little bit trickier. Remember, what we've seen is that p double prime, the second derivative of 2, well, that's going to be equal to 2c2. And if we want that to equal -1/2, here's where you have to solve that super simple equation, just divide by 2. Our c2 is going to not just be -1/2, but it's going to be -1/2 over 2 factorial, which I can write like over 2 factorial, but I would just simplify that to -1/4. And the third derivative of p, and this is where we have to remember our formula, that at every step of the way, the derivative, sorry, that n is supposed to be in the superscript up here. The nth derivative of a is equal to n factorial times the coefficient. So p3 of 2, I shouldn't say p3, the third derivative of p evaluated at 2 is equal to 3 factorial times c3, which means that c3 by itself would have to equal this, that negative 2, the third derivative of f, over 3 factorial, or negative 2 over 6. And so what we're seeing here is another example of the formula we saw with that sine when we found the Taylor series for sine. This idea that at any level, the coefficient in front of the term of the nth degree is going to be the nth derivative of f evaluated at whatever point we're evaluating. In this case, that is just 2 divided by n factorial. And so we can see that's what this C3 was. It was the third derivative of f evaluated at 2 divided by 3 factorial. So now we have, for our Taylor series, we have all of our coefficients. C0 is equal to 1. C2 is equal to 3. Sorry, C1 is equal to 3. C2 is equal to negative 1/4. Might as well put the negative in there. C3 is equal to negative 2/6, which might as well call that negative 1/3. But here's where you have to be a little bit careful. The Taylor series we've seen so far were all Maclaurin series centered on x equals 0. As soon as we see another number here centered on x equals 2 instead of x equals 0, what that means is we're going to keep seeing, instead of just plain old x to the first, x to the second, x to the third, we're going to see x minus 2 to the first, x minus 2 to the second, x minus 2 to the third. And if this Taylor series needed to keep going, it would, but keep in mind here that every derivative after this is going to be equal to 0. So my C4 would equal 0 over 4 factorial. My C5 would equal 0 over 5 factorial. C6 would equal 0 over 6 factorial. And it'll keep going like this. All of these terms will just be 0, so we don't need to worry about them. And so this is the Taylor series that we're looking for. It is really easy to overlook the fact that we had to change the way the series looked a little bit by putting x minus 2 in everywhere. So make sure that every time you see that 2, it's going to show up in 2 places. It's going to show up as the number that we plug in to find the derivative. Right, we need to plug that 2 in there. And it's also going to show up again in that x minus 2 every single time and for every single term. You might be asking, wait, what about this first term? Where's the x minus 2 there? Well, that's because it's x minus 2 to the 0 power, because that was our C0. And so if I wanted to write this out as a quick formula, I could put that formula for C sub n, the nth derivative evaluated at a divided by n factorial, times x minus a to the nth. And that is how I write a Taylor series. So let's do that for an example, which is going to look pretty similar to one we've already seen, but with a bit of a difference. We're going to find the power series for y equals sine of 2x evaluated at, or I should say centered at, x equals pi over 2, which is going to make things only a tiny bit more difficult than what we saw before. First things first, though, we need to know the derivatives and second derivatives and all of that of sine of 2x, and then evaluate them at pi over 2. So we'll start with f of x is sine of 2x, f prime of x, and I again gave you one where the derivatives should be pretty easy to find. Remember the chain rule, 2 times the cosine of 2x, and the second derivative, Remember the chain rule again, we're going to have to keep multiplying by 2 every time. This one, though, this sign becomes negative. And so we still have a negative because we're not changing the sign again. But then when I go to the fourth derivative, we're going to change the sign again, so now it's positive. And then for the fifth derivative, this will be the last one I put down. We're again going to keep the sign the same because the derivative of sine is positive cosine. And now we can evaluate all of these at pi over 2, which might be a little bit more annoying than evaluating them at 0, but I still gave you one that's easy. It's pretty easy to evaluate, sine, cosine, etc. when x is pi over 2, especially because in each case we're multiplying that by 2. So the sine of 2 times pi over 2, and that 2 times pi over 2 is going to happen every time. It's just going to equal pi. So the sine of pi is 0. Sorry, I wrote of 0 there, but that was wrong. F of pi over 2 is equal to 0. And f prime of pi over 2, well, this time it's the cosine of pi, which is negative 1, with a 2 in front of it. And f double prime, well, we're back to the sine of 2 times pi over 2, which is 0 again. And then for the third derivative, it's back to the cosine of 2 pi over 2, which is negative 1. But now there's a negative 8 in front of it, so it's actually positive 8. And the fourth derivative of f evaluated at pi over 2 is 0 again, because again it's the sine of 2 pi over 2. And then our last one, the fifth derivative of our function evaluated at x equals pi over 2 is 32 times the cosine of pi, which is negative 32. And remember, once we have these derivatives, finding the coefficients from them should be easy because we have the formula to use. C0 is equal to f of prime over 2, of pi over 2. C1 is equal to f prime of pi over 2. C2 is equal to f double prime of pi over 2 over 2 factorial. I'll write that down. F double prime of a over 2 factorial, but in this case that's just 0 because f double prime of a is 0. And C3 would be the third derivative of f evaluated at pi over 2. That's the 8th that we already have, over 3 factorial. C4 will be 0 over 4 factorial, and C5 will be negative 32 over 5 factorial. And so we can turn those into our Taylor polynomials simply by putting the x minus a attached to every coefficient. Now, I don't need to worry about it for the C0 because that's 0. But the first term is negative 2 times x minus pi over 2 to the first power. Then I'm going to skip the quadratic term because C2 is 0, plus 8 over 3 factorial times x minus pi over 2 to the third. Skip the fourth degree term. The fifth degree term is negative 32 over 5 factorial times x minus pi over 2 to the fifth. And this is what we would call, the directions would call this the first 3 non-zero terms of the Taylor series. This one does keep going forever. If you were asked to put it into sigma notation, your job would be to recognize the patterns. First off, I'm going to start with n equal to 1 this time and go to infinity. The reason is because I start with a negative And so if I start with -1 to the nth power, that needs to start with n equals 1 instead of n equals 0. That's how we start with a negative number. You certainly don't have to do it this way, but that's the way I'm going to. And then each of these coefficients, notice the 2, 8, 32, well, that's just powers of 2. 2 to the first, 2 to the third, 2 to the fifth. And so I need to figure out a way to write those odd numbers. We saw that earlier, odd numbers. We can write them as 2n plus 1, or in this case, it needs to be 2n minus 1, because I'm starting when n equals 1. So the first 2n would be 2 times 1. But if my first exponent here is 2 to the first, I need to subtract 1. The rest of my coefficient here is over that same 2n minus 1, that same odd number, factorial, times x minus pi over 2 to the same odd numbered exponent, 2n minus 1. So notice that 2n minus 1 appeared all over the place there. And that is the power series for sine of 2x evaluated at pi over 2.